All right, so this is the second part of chapter 22, kind of the first part of unit 9. Okay, so now we're going to talk about batteries. So as mentioned yesterday, or in the previous video, a capacitor releases charge really quickly. Okay, a battery takes time. It actually controls the rate of charge that moves from one end to the other. So it controls its rate of potential difference loss. So the inner workings of a battery, you can think of it like a charge escalator between the two terminals. So the charges are removed from the negative terminal and lifted to the positive terminal. Okay, so we have these charges that lift up, and then the charge moves through it. Okay, so the potential difference of the batteries across it like this. So the positive charges build up as you go from one spot to the negative side to the positive side. So that positive terminal has a big amount of charge that kind of gets pushed out all the way back around. So the charge escalator battery sustains the current while providing a constantly renewed supply of charges to that positive terminal. And then once that charge reaches the positive terminal, it'll flow, essentially downhill in terms of potential difference. And that flow of the charge in a loop is called a circuit. So charge escalators in batteries powered by the chemical reactions called electrolytes. The electrolytes are put in between the positive and negative material. And that chemical actually acts to move the charges. And when that electrolyte, or when the charge is exhausted, the battery is dead. A reusable battery can flip the charges around, so that it can be used again. So by separating charge, the charge escalator establishes the potential difference between the terminal of the battery, which is what you need. No potential difference, no movement of charge. Okay. So EMF is your electric force in the battery, which forces things to move through it. So a rating for a battery is the battery's EMF, the voltage. Okay, a battery with no current in it has a potential difference equal to its voltage, its EMF. With a current, the battery's potential difference is a little bit less. Okay, and here we're going to basically just say that the voltage of that battery, the potential difference, the differences in that electric potential of either end to want the charge to move is equal to your electromotive force. If you get into more higher level classes, they'll go into the differences. So we have three batteries that are connected. We can say that this is called a series of things when one's connected to the end of the other one. And if you notice, positive to negative to positive to negative. This is in series, so we have a total now potential difference that you just add up. So this gets a bigger potential difference. So if you line up batteries in a series like this, or if you think about when you plug things in, when you put batteries into something, typically they alternate the sides that they point to, so they can keep the wires, make sure that these batteries are wired in series, so you have a bigger potential difference. So a bigger potential for charge to possibly move through it. So these could be double A's, triple A's, C's, and D's. They all have 1.5 volts. The only thing that really differs from in each of those is what the rate of current that's allowed to move through them is. Okay. So you can do this. You can actually conduct this experiment. Many of you don't have these anymore with the actual headphone jack in there, but if you have a headphone jack, you can hear a soft click of the potential differences causing the current if you put a penny next to it. All right, so that was a quick version for 22.3. So really the batteries provide the potential difference for that charge to get moving through the circuit to create a current. Now we're going to look at that electric potential and current. So like we said, the battery is that source of that potential difference in the circuit. So because the ends of the wires are connected to terminals, the potential difference between the two ends is the potential difference of the battery. Okay, and then thus it becomes the potential difference of the wires in the circuit. And that potential difference causes a current in the direction of the decreasing potential, from where there's high potential to low potential. So there's two things that determine the current, that voltage, and then the properties of the wire. And so the bigger the potential difference, the bigger the current. So adding a second battery increases the potential difference, which increases the electric field, which makes more current. So if you increase the length of the wire, you decrease the amount of the current in a given spot. And if you make it thicker, you increase the current. Okay? So in order to get a really good current, you want a short, wide wire. If you have a long, really thin, skinny wire, you don't get as much current. The current gets much less. So wires of different materials carry different currents. Copper carries a lot more current through it than iron. Okay, so the materials are better. The better the conductor, the better the current. The whole thing about the better the current really is involved in this thing called resistance. Resistance is simply how hard or easy it is to push charge through. A bigger resistance means it's harder to get more charge through a wire, harder to get more current through a wire. And the current depends on the resistance of the wire and the potential difference between the wire ends of the wire. So we have this equation that says current is equal to the potential difference of the wire divided by the resistance of that wire. So you can see the greater the potential difference, the greater the current. The greater the resistance, the lower the current. Think of it like people in a hallway. If you can get through a kind of a wider hallway when there's not as many people, you can go really fast through it. But if you put more obstacles in the hallway, you don't move as fast. Your current decreases. Your rate that you move can decrease. Okay, so this is called Ohm's law. Resistance is voltage divided by current. Okay, and the resistance, the symbol, the unit for it is ohms, and it is the symbol omega. So 1 ohm of resistance is 1 volt of potential difference divided by 1 amp of current. So the more resistance you have, the harder it is for current to move through it. So flowing of an element, the glowing element in an incandescent light bulb is a long piece of wire from an element called tungsten that's heated by the current. Okay, so when it's connected to 120 volts of an electric outlet, which is what you have, your outlets in your house have a potential difference of 120 volts. A 60-watt light bulb carries a current of a half an amp. What is the resistance of the filament of the lamp? So if we look at this, resistance is voltage divided by current. We have 120 volt potential difference and a half an amp of current. That gets us a resistance of 240 ohms. Okay, and the resistance of this thing kind of varies on the temperature. And you'll see that the different temperatures have different resistances. Another characteristic, along with resistance, is this thing called resistivity. So resistivity characterizes the electric properties of the material. Good conductors have low resistivity. Insulators have high resistivity. You can think of it resistance, resistant to that charge moving through. Okay. And the resistivity of the metal decreases with increasing temperature. When you increase the temperature, it's easier for charge to move through it. So resistivity of material looks like this. So copper has a really, 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 really low resistivity. Okay. Water, relatively high resistivity. Okay. Again, it's the electric properties of the material to resist, to to not allow charge to move through it. So resistivity goes into looking at the resistance of a wire for certain conditions. The resistivity pretty much remains constant, okay? But the resistance of a wire, the formula for this is resistance is equal to resistivity times the length of the wire times the cross-sectional area. So if you look at this, the longer your length, the more resistance you have. The wider a wire, the less resistance you have. The wider the wire, the less resistance you have. So we have these. A filament of 100-watt lead bulb carries a current of 0.83 amps at a normal operating voltage of 120 volts. What's the resistance of the filament? And if the filament is made of tungsten wire of diameter 0.035 millimeters, how long is the filament? So we know that this 100 watts, that's power. That's the rate that you transfer energy. There's your current, there's your voltage. So we have since we have power is voltage squared divided by resistance. Okay. The cross-section area, now we've got to look at how to find the area. It's pi times 3.5 times 10 to the negative fifth divided by 2. The diameter divided by 2. Pi r squared gets us our cross-sectional area. Okay, so we can look at the resistivity of tungsten when it gets hot. Up here. 5 times 10 to the negative 7. So we have our resistivity, 5 times 10 to the negative 7. We have the diameter. Okay. Since we have voltage and current, we can find resistance. Since we have back here, resistance is voltage divided by current. So resistance is voltage divided by current, 120 divided by 0.83. To get 145 ohms of resistance. So now we have resistance. We have our cross-sectional area. We have our resistivity. We can figure out our length. So resistance times area divided by resistivity gives us our length. Okay. So I would look at this chart, and you can look at resistivity of just about anything that's on here, and use that to figure out other items. Okay. So we have this one. Example up above that a 60-watt light bulb has a resistance of 240 ohms. At the operating temperature of the tungsten filament, the resistivity is about 5 times 10 to the negative 7th ohms meters. If the wire used to make the filament is 0.040 millimeters in diameter, how long must the filament be? All right, so we're going to use the length is equal to area times resistance divided by resistivity. Rearranging the initial equation. So we know our area, because area is pi r squared. Pi times our radius squared is 1.26 times 10 to the negative 9th meters squared. We know our resistance, got that earlier. We are given our resistivity from the chart above. So 1.26 times 10 to the negative 9th meters squared times 240 ohms divided by 5.0 times 10 to the negative 7th ohm meters gets our length to be 0.6 meters, 60 centimeters. resistivity in tungsten is really low, so the filament must be quite long and thin. Okay, so different tissues in the body have different resistivities. Fats have a higher resistivity of the muscle, so a higher resistance in the body indicates a higher proportion of fat. That's actually one of the ways that they can figure out body mass. So different body types can actually give out different resistivities, and you can have different conducting areas that look like this. To look at resistances in electric charge. So Ohm's law, we showed you this earlier. Except when I showed you it was resistance is voltage divided by current. Current is voltage divided by potential difference divided by resistance. Okay. Now here's an interesting thing. Ohm's law is not a law of nature. It's limited to those materials whose resistance remains constant during use. Okay. So if the resistance is not constant, it's not what's called an ohmic material. So if the resistance changes, it's called a non-ohmic material. So the current through an ohmic material is directly proportional to the potential difference. Okay. So if it's non-ohmic, that means that the current moving through the device is not directly proportional to the potential difference. Capacitors and batteries are non-ohmic. They don't completely follow this. Most light bulbs do, not batteries and capacitors. So, talked about batteries, talked about wires. Now, light bulbs and other things that you plug into a circuit are called resistors. Things you put into a circuit that are designed to have certain resistances for use. Okay, they're going to slow down the flow of charge. So as charges move through a resistive wire, their electric energy is transferred to thermal energy. So the higher the resistance, basically the more energy gets taken out of the circuit. Okay. So if you look at most electronic devices, you see things that look like this. These are resistors, and these different colored bands is a number scale to indicate how many ohms of resistance there are. And if you ever taken electrical wiring class, they'll actually teach you the color band ratings for these to show you with these color bands what the different resistances mean. Okay, and then we can have resistors whose resistance changes in response to changing circumstances. So like the sensors. Okay, those sensors have different resistors in them that adjust to the current, and if the current gets too high or low, it turns off or on. All right, so we have an electric blanket that has a wire running through it. So we put the low voltage electric blanket is rated to be used at 18 volts. It dissipates a power of 82 watts of power. What's the resistance of the power that runs through the blanket? So power is going to be V squared divided by R. Power is voltage squared divided by the resistance, which is equal to 82 watts of power. So resistance, resistance is V squared divided by the power, which is 4 ohms. I'm going to skip through this one. All right. So when you press the lever on a toaster, a switch connects the heating wire to 120 volts. The wires are initially cool, but the current of the wire raises the temperature until they are hot enough to glow. As the wire heats up, how does the current in the toaster change? I think many of you have probably seen this. Toasters start off dark and then they glow when it gets hot. So as the wire heats up, its resistivity increases. So the resistance of the wire increases because because the delta V stays the same, increasing the resistance also causes the current to decrease. So actually, the most current goes through when the toaster is first turned on. After that, the current decreases through it when the element heats up. As the wire's temperature increases, the current decreases. This makes the system stable. So if the current increased as the temperature increased, the higher temperatures could lead to more and more current, and the toaster would overheat, which is not good. You want to have a good temperature for that. So in a light bulb, connections to the filament are made at the tip along the side of the metal here. Okay, and part of the reason that the filament works is that the inert gas creates part of the glowing. So the current moves through the wires, goes through this filament that has a relatively low resistance, that heats up and reacts with the inert gas a little bit to make it light up. So in the circuit with a battery light bulb, battery has a resistance of about, the light bulb has a resistance of about 3 ohms. Okay. Now the interesting thing with this, if we look at the voltage moving through things, the voltage across a resistor drops. That means the potential difference drops across a resistor, which means that the potential difference is the highest right as the current comes out of the battery. So every time you put a resistor in there, you drop the voltage that goes onto the next wire. So there's a voltage drop when the current passes through a resistor, and this happens every time. There's a voltage decrease. So the more items you put on a circuit, the lower you drop the voltage for the ones at the end. Now, there has to be an electric field. There has to be a field of influence of electric charge on the wire in order for the current to move through it. There has to be something pushing the charge along. And this electric field is the potential difference divided by the length of your wire. So the greater the voltage, the stronger this electric field. The longer the wire, the more that electric field drops. So you want a relatively short wire to have a really big electric field. We're not going to look at this one. Okay, the last section is on energy and power, and this one's actually relatively quick. Okay, they also supply energy. Batteries supply energy and potential difference. Okay, so this charge escalator transfers energy to potential energy to useful energy. Okay, the charges gain potential energy, which is actually used to power things. And power is current times voltage. Okay, the power in this is really how fast electric charge gets converted to something else, which is a watts of power. Okay. So we have current divided by time. Charge divided by time, which is your current. Current times your voltage gets you your power. So power is the current that moves through there times that voltage. Your EMF, your voltage. Okay, so a car battery has a potential difference, your EMF, of 12 volts. When the car starter motor is running, the battery's current is 320 amps. What power does this generate? You just multiply them together. So the greater the current, the more power you have. the greater the EMF, the electric potential, the more power you have. So in a circuit consisting of a battery and a single resistor, the entire sequence of energy transformations looks like this. We have chemical energy in the battery, which gets converted to potential, which gets converted to kinetic, which then gets converted to thermal energy. Chemical energy in the battery ultimately transfers to heat energy in the light bulb or something, or a resistor. So let's you look at this thing here. We have the escalator, which moves the charge, then pushes the charge out through the wire. Then we hit a resistor that takes energy out. Kinetic that gets transferred to that kinetic energy as the electrons collide in there. That releases some of them with that thermal heat energy, which causes your resistor to heat up. And those of you that can feel your phone chargers on certain times, they heat up. Okay. So net result of a circuit consisting of a battery and single resistor is that the battery's chemical energy, as we said, is transferred to thermal energy, raising its temperature. The rate that the energy transfers from the current to the resistor is this. So power is change in energy divided by time, just like it was with mechanical power. This change in energy is your current times your potential difference, which is your current times potential difference of the resistor. Oops, sorry. So in a single resistor circuit, the current is the same in the battery and the resistor. Notice how it says single resistor circuit. The power dissipated in the resistor is exactly equal to the power supplied by the battery. And the rate at which the battery supplies the energy is exactly the rate that the resistor dissipates that energy. So the powers are equal. So how much current is drawn by a 70-watt light bulb connected to a 120-volt outlet? All right, so the light bulb's a resistor. It takes current out of the circuit. So because the light bulb is operating as intended, it'll dissipate 75 watts of power. It says so right here. So current is power divided by voltage. We just rearranged the previous equation. So 75 watts divided by 120 volts is 0.63 amps of current. And most current that moves through most things in your house is right around an amp or a little bit less. So that means that's reasonable. So resistors are ohmic materials, so they obey Ohm's law, I equals V over R. So we can say that power is current times voltage. Because resistors are ohmic, for I, we substitute I as V over R. Excuse me. No, sorry about that. We substitute V squared as I times R. So then we have I squared times R. And we can then substitute from I squared to get V over R. V squared over R. So power varies as the square of both the current and the potential difference. So depending on what you have, you can use these equations. But power is simply just the rate that energy gets transferred from chemical to thermal energy. So we have this power. We're getting close to a 30-minute video here. This is just a sample problem. If you want to pause and look at this, feel free. And that's the end of the video. There's a lot of information here. I would go through and read your book along with watching this video to get more information. And please, please, please ask questions at the bottom of the video. We'll see you in class.